Hi everyone, welcome to my channel. My name is Chris Chen. I'm the CTO of Issues Technologies. And in today's video, I'm going to show you how to test tubes with the emini, the vacuum tube tester for small signal tubes. And this is a latest project I've been doing for the past few years. In my previous video, I already showed you the system architecture and the test mode this tester can do. So today I'll show you a real demo on for each test mode. Okay, so this is a board and this is a prototype now. It's a full functional prototype. So it comes with all the bells and whistles, like I introduced in my previous video. So let's have a look at the top panel. So here we have the LCD display. This is a 2.8-inch IPS LCD display, so it has a very wide viewing angle. On the display, on the first row is the DUT type. So here we currently it shows 12x7 and 7/15 means there's already a 15 config file flashed in the stored in the flash memory of the microcontroller, and this is number 7 of the out of 15. And the first block here is settings. Settings means the values we're going to apply on the DUT, like the plate voltage, the grid voltage, the heater voltage, and the plate current, etc., etc. The second block is the readings. This is a feedback from the ADCs, analog to digital converter. So from those from the reading of the ADC, we can have the current voltage, high voltage, current grid voltage, current plate voltage, current heater voltage, heaters current, and the plate current. And the last row in this block is power consumption. So there it has 3 values. The first one is the plate consumption. The middle one is the power consumption on the constant current source. As I showed in my previous video. There is a innovative configurable high side current source connected to the plate of the DUT. It can act as a very high impedance plate load. So for the amplification to form an amplification circuit, and so it will consume some power because we are going to apply a voltage across the constant current source. And the last one is the total power consumption. It's a sum of both values. Okay, and the third block is the test result block. The parameters shown here varies by different test modes. So currently we are under a microphonics mode, test mode, as indicated at the bottom row. And so we see there's a plate signal VRMS. This is a gain VRMS, and the gain in dB and the linear gain. And we have the sound level meter here. Sorry, sound level meter. Yeah. Okay. So so you can see this block will give you different rating with different test modes. So here we are in under voltage based parameter extraction mode. So it will give us the different readings like GM, mu, and RP. Okay, here we have 3 LEDs. This one is a system power. This one is a heater on indicator, and this is a high voltage on indicator. And followed by 3 rotary knobs. The first one is a DUT selection knob. So by turning this knob, we can select. If we follow the first row, we can select different device under test. So today we are going to test. The first tube we're going to test is a 12AX7. So let's put it at the 12x7. So this one is a test mode selection. So if we can select different test mode here. Currently we have the total of 5 test mode, I think, or 4. We have voltage-based parameters extraction mode, current-based parameters extraction mode, gas test, microphonics, manual mode. This is only for internal test. Okay. And this one is a section selection. We know for small signal tubes, there's a lot of twin triodes, so it has two sections inside one envelope. So these knobs allow us to select which section we want to test. So we can select from section A, section B, and A plus B. It means the two sections will be connected in parallel. And if we rotate all the counterclocks all the way, we can select nothing connected, indicated by these 3 dashed lines. So let's put it under. Oh yeah, one thing to be noted is that for parallel connections, the current gain is doubled, the internal resistance will be halved, and the gain will remain the same. So if I select B, between section B and section A plus B, you can see the system will automatically update the reference value of the parameters. So for 12x7 under this operating quiescent operating point, the transconductance value should be 1600 for one section, and the internal resistance is 62,000. So if we put the position of this knob at the A plus B, we can see the transconductance value, the reference transconductance value is doubled, and the RP is halved. Okay. And here we have 4 push buttons and the rotary knob here, and this allows us to do a voltage adjustment or current adjustment on the fly. So this one is a heater voltage adjustment. Okay, so here it allows us to adjust the voltage of the heater's power supply, and the increment by default is 0.1 volt. So if you push this button, you can select the increment of 1 volt. I mean, it depends. It varies like setting by settings. Like, so if you want to adjust different values, the increment is the increment can be selected accordingly. Okay, this is a vibration motor voltage adjustment. This knob is not implemented. This button is not implemented yet. This one is a high voltage related adjustment. So under this test mode, voltage based parameter extraction mode, only the play voltage can be adjusted. And if you select the current based parameter extraction mode, we can change both the plate voltage and plate current. Okay, and this is a negative grid voltage selection. Okay, and here on this side we have 4 push buttons. This one is heater on off, and this one is a high voltage power supply on off switch, and this is vibration motor power switch. This only works under microphonics mode, and this is a test button. So here we have a BNC connectors, and it's the signal comes from the plate of the device under test. So we also have a built-in sinusoidal waveform generator, so we can observe waveform on the oscilloscope. We also have a built-in loudspeaker here, and we have a volume control knob here. So we'll have a look at those. We can hear the noise later when we do a microphonic test. And this is a vibrating motor, and here we have 2 sockets for different type of tubes. We have a miniature 9-pin socket, and the wiring is for 12AXS7 related tubes like 12A7, 12AU7, or 60J8. Here we have an octal socket. It's not mounted yet, so this socket is wired for 6SN7 family type of tube, 6SL7. Okay, so for testing other type of tubes with different pin out, then we need to use adapter. So I'll show you guys later. Okay, that's pretty much the layout of the operating panel. One thing to mention is anytime we change the setting, we'll see a star sign next to the name of the device under test. It means the parameters are tempered. So anytime we want to go back to the original setting, we just push the button of the duty selection knob, and it will reset all the parameters. Okay, so now we are ready to do some tests. So the first tube we're going to test is a 12X7. So we already have our device selection, the duty selection to select the 12X7. So we can now turn on the heater supply, and we can see the heater, the LED for the heater supply is on. Now we can turn on the high voltage supply. And here we can see two values. We have a plate voltage and the high voltage. They are slightly different. The reason for that is the high voltage supply is after the high voltage supply is generated, it will go through the constant current source and some internal resistance and some transistors. So the actual voltage appear on the plate will be lower than the high voltage supply. So the firmware will automatically adjust the value using a update algorithm to keep the plate voltage set to our desired value. Okay, so the voltage-based parameter extraction mode is how to say the de facto method of extracting vacuum tubes parameters. So it's pretty much how all the tube tester does. You set the plate voltage, you set the grid voltage, and then you take the readings under that quiescent operating point. So the reading includes the plate current. So here we can see the plate current is 1.38 milliamp. The reference value is 1.28 milliamp, and now we can run the test. To test it is really simple. Just push the test button, wait a couple seconds, and the reading will be shown on this block. So we have the GN, and we have the mu, and we have the internal impedance RP. It's that simple. Okay, so next we can switch to the current-based parameters extraction mode. This test mode is unique to this tube tester. It's never implemented before, and the idea came from the discussion I had with the owner of the Jack from Dave Wallace, the owner of Jack Music and Emission Labs. He believes that the parameter should be extracted at the specified plate current instead of the specified plate voltage. So this mode is basically under this mode we configure the plate the constant current source so to confine the current to be exactly at the reference. For our example, it's 1.2 milliamp, and the plate voltage will be kept at 250 volt, and the firmware will update the grid voltage until the condition is met. So I like I said in my a couple times, I am not totally agree with the idea of the how the parameter extraction should be done at the specified plate current, because for a very weak tube, you might need to like make the grid voltage much less negative to boost the play current. And the problem with that is even you can get the decent readings on the GN or RP, you actually sacrifice a lot on your voltage swing. So but anyway, this is this is a mode that allow you to do that. So every time we change test mode, you can you probably notice that the high voltage LED is turned off and the heater supply remains on, because between different test mode we might want to change the high voltage setting differently. So as a precaution, we always the machine always switch off the high voltage supply, so we need to turn on the high voltage supply manually. Okay, and you probably notice that the reading is not does not match the setting. There's a couple like 1% or 2% errors. It's because this machine is not calibrated yet. Okay, so instead of 1.2 milliamp, we can see the reading is only 1.1 milliamp, and I mean that's due to the still it's the constant current source is the hardware believe is configured 1.2 milliamp to the hardware, but because it's not calibrated, so let's ignore that for a while. Okay, and now we are ready to extract the parameters under this quiescent current, and you can see the because this tube is strong, so the system actually need to bring the negative the grid voltage to more negative to lower the plate current. Sorry, to bring the plate current to a lower value. Okay. Test under this mode is quite easy. Just push the test button, and a couple seconds it will give you the readings. Okay, so now we are ready for the next mode. The next mode is gas test. Gas test is done by connecting two different values of resistor to the grid electrode of the device under test. So now still let's turn on the high voltage supply. Okay, so the value for the two resistor, one is 2k ohms and 1k ohms, and the other one is 180 ohms. 1k ohms and 180 kilo ohms, and the system will try to the system will measure the difference of the plate current and try to play with the grid voltage until this plate current are equal again. So in this way, by observing the difference of the grid voltage and the difference in the plate current, it can derive the grid current. Okay, so the gas test mode is a test to, actually it's not it's a gas test, but the idea was to test if the tube is gassy or not, but actually it's more a grid current test. So we I think I have article on the issue on the issues website describing the different grid current induced in a vacuum tube. So by looking at the grid current is not a good way to identify whether a tube is gassy or not. But anyways, this is how the value the value of the resistor are selected to match the value used in a TV7 vacuum tube tester, and the difference between this tester and the TV7 and the TV7 is the gas test mode for on this machine. Like I said, you can set the quiescent point at any value you want, and you can check the grid current at under that operating point. So it's for TV7, it's only test the grid current at the fixed operating point. So now we can do a test. Here we can see the plate voltage current difference is 5 microamp, and the grid voltage difference is so small that the grid current is negligible. Okay, so that's because the negative voltage is actually is quite low. So we know that when the grid voltage close to 0 volt, is the higher the grid current. So we can play with that, and now we can, for example, we can change. Before we do that, we have to be very careful. We don't want to make the plate dissipation so high that it exceed the rated value. So the first thing we do is let's see, we can lower the plate voltage. Okay, then we can adjust the grid voltage safely. So let's put it at -5 volt. We can see the power, the plate power consumption is still stays at the 0.3 watt. So it's safe. And if we do a test now, we can see, yeah, the plate current difference is higher, and we can the derived grid current is higher. Okay, so that's gas test. Next, as microphonics test. This is a very interesting test mode. Okay, turn on the high voltage power. I think we need to reset the parameters. Okay, so under this mode, the constant current source is connected to the plate of the DUT, and there's a approximately 30 volt voltage difference applied on the across the constant current source. So this circuit is now acts as an amplifier. So we can here we can see the VRMS, the signal, because there's no signal applied now, so this is actually the noise of the system, and we can hear the noise floor by cranking up the volume of this audio amplifier, and we can hear the sound from the loudspeakers. Okay, and the test button is no longer a test button. It's now a switch for the sinusoidal signal generator. The signal output is fixed at the 442 hertz. It's an A note, La in C major. Okay, so now we can hear the tone. And here we can see the audio is the output is clipping because we cannot the system, because the voltage applied across the constant current source is not much, so we need to reduce the signal level. Okay, when the signal level is low enough, the system will calculate the system gain in dB and the linear gain on the fly. So here we can see the linear gain is approximately 95, something like that, and the assist in dB is close to 40 dB. Okay, and also, like I said, we have a BNC connector, so we can observe the waveform on the oscilloscope with a BNC cable, coaxial cable. All right, so let's turn off the signal. And so how to test do a microphonic test? We can use the old brute force method. We can like I said, we have the sound level meter here, so we can just tap the envelope, and by observing the signal difference before and after the shock is applied, we can set the threshold, and we can identify how bad the this DUT is influenced by the vibration. The second one is more civilized way, and it gives you a more like constant shock to the device under test, so you can compare the different tubes in a more fair way. So this is how we do it. We can use the vibrating motor, and still from the reading we can see the sound level before and after the shock is applied, and that's the one way we can we tell how microphonic the device under test is. Okay, we are done with 12X7. So next time, the next tube we are going to test is is a 6C45. So let's select 6C45 as a device under test. So here we need to use this adapter to test the 6C45. Plug in, turn on the heater. So I'm going to test this tube with under the voltage based parameterization mode only. So to save time, and we can turn on the high voltage supply now, and we can see the plate current is increasing. For this kind of tube, we should actually allow a longer time for it to warm up, but for demo purpose, I'll just test. As you can see, the plate current is still increasing, but I just push the test button, and we can see the readings and the percentage here. It's very simple. Okay, so this is about it for this video, and thanks for watching my channel, and I'll see you next time. Bye.